How's it going, everyone? How are y'all doing?
Good. How about you?
I'm pretty good. Chris, how are you doing today?
Great.
I'm actually checking your audio when I ask you to say something. That's my trick there. It's like, oh, how are
Okay,
you?
okay. Yeah, I'm doing great.
All right. Summer, how are you today?
I'm doing excellent. Thanks, Doss. How are you?
Oh, I'm pretty good. Thank you very much. We've got everybody on the stream, so it's time for our main event here, talking about sounds in space. Really quickly, before we get going here, I want to make sure everybody understands the streams don't just do themselves. There is a lot of work that goes into it, a lot of organization and stuff like that. This month's Intrepid Museum Virtual Astronomy Live is made possible by the New York State Council for the Arts with the support of Governor Andrew M. Cuomo and the New York State Legislature. So thank you so much for the sponsors for making these things possible. Let's go ahead and get going here, shall we? Summer, take it away. You're in charge.
We shall. Thanks, Doss.
All right.
Hi, everybody. For anyone who has not joined one of these before, my name is Summer Ash, and I am a science communicator who also has been an engineer and an astrophysicist and just loves space in general. And so I get the awesome job of moderating these events. And today we're going to be exploring sounds from space. But when we say that, everybody should know that sound does not travel through space because it's a vacuum. But we still have a ton of really cool sounds made by things that are in space. I am joined today by Dr. Alexa Halford. She is a research scientist and the associate chief of the ITM Physics Laboratory in the Heliophysics Science Division at NASA Goddard Space Flight Center. And I had to Google ITM, which is ionospheric, thermospheric, and mesospheric. So we're gonna get into that later because I don't remember much from my probably middle school and high school atmospheric sciences. Also joining us today is Dr. Kristine Sigsbee. She is an assistant research scientist in the Department of Physics and Astronomy at the University of Iowa in Iowa City, Iowa. And I kind of want to start off just by getting a little bit of context and background to how each of you got into what you do. And then I just want to start listening to sounds and having fun. So Chris, do you want to sort of tell us just how you got into physics and heliophysics and space physics and all that good stuff?
Sure. I grew up in northern Minnesota, and one of the neat things that we could do up where I grew up was see the northern lights. And I got interested in, what made the northern lights. And so when I went to college, I found out, hey, this is something that you can study and do for a living. So that's kind of how I got into this.
That's super cool. What's your focus? What's most of your research on these days?
Lately, I've been doing work on Earth's radiation belts, which are very important for an emerging field called space weather, because we depend on a lot of technology like our GPS navigation, communication satellites, and of course our electrical power system. And we're trying to understand how the sun and Earth's magnetic field affect these things.
Yes, and speaking of radiation belts, I forgot to mention the fun fact of the fact that Iowa is also the birthplace of James Van Allen of the Van Allen radiation belts, right?
Right, and he also was very important in launching the first U.S. satellite, Explorer-1.
Oh, I did not know that. Was he at the University of Iowa as a researcher?
Yeah, he was, and actually he discovered the radiation belts using a Geiger counter that was on Explorer-1.
Oh, that's awesome. I did not know that. And Alexa, how did you get into ITM?
ITM, yeah, it's been a long, winding path for sure. I always knew I wanted to be in science as a kid. I loved just learning and exploring the world. I remember being very young and seeing a butterfly move its wings, and I thought, I'd expect to see 2 wings, and instead I saw 4, and that was incredible and crazy. And that discovery was like, that sense, even though tons of people knew this way before me, it was still cool that I myself, and that really drove me into the sciences. I then also ended up in Minnesota I went to Augsburg College, where I got to study space physics. I had no idea what it was. And my professor gave me a ton of files to look at, a ton of pictures that had all these colors on it, and I didn't know what anything was. He told me that after going about through a month of data, I'd probably figure out what was interesting. Uh, so I came to him the next week and said, here's this thing that happens in the morning, and it seems to happen in both hemispheres, and it's really cool. And he goes, oh yeah, that's the aurora. We already know all about it. And so, well, I thought that was really cool that I had once again discovered something that tons of people had known about for years and years and years. That sense of discovery and just, you know, learning something new that I didn't know before, and that kind of set me on my path. I then went on to graduate school and studied radiation belts and waves in space, and then came to Dartmouth College, where I did my postdoc and learned about how those waves pushed particles down into the atmosphere. And that's really what led me down further, along the field line, the magnetic field line. As my dad always liked to say, I went to college and took up space, and I still have my head above the clouds, you know?
I love it. I love it. In my field, I think it's true in most of astronomy, but in radio astronomy, like a guaranteed question that you can ask at any given talk that will make you seem smart is, have you considered the magnetic fields? Because no one really knows the answer to that. Okay, so did you get to see some aurora while you were at school in Minnesota?
I did, and I saw aurora when I was a kid. I grew up in Wisconsin, so another Midwest gal. But it's just fantastic. Anytime you get a chance to really see the aurora and go and look at it, I'd say jump on it, take it. You know, I was really lucky to see the aurora when I was down in Colorado. It's a very different experience there than it is when you go up north. In Colorado, you're at such a low latitude that you typically see these red auroras that look more like burning fires instead of the green rivers that you see up north. And so that's really kind of a fun experience too, seeing how the aurora changes. One year I actually got to see the aurora from a plane. It was around this time of year. I was flying off to the American Geophysical Union, where lots of people go and talk about their studies of the aurora. And I looked out the window, and sure enough, there it was. So I've always then tried, whenever I'm flying from the East Coast to the West Coast or vice versa, sit on the poleward side of the plane. So if you're flying from Boston to San Francisco, you want to sit on the right-hand side of the plane. And if you're flying back home, then you want to sit on the left-hand side of the plane.
That's funny, because I always want to sit on the other side of the plane, because then I can see the ecliptic and look for the planets and the constellations. The difference between the green aurora farther north and the red farther south, does that have anything to do just with like kind of refraction, or like the scattering the wavelengths?
So it definitely has to do with the wavelengths, and it's what energy particles are hitting what particles in the atmosphere. And so you might be hitting an oxygen, or you might be hitting a nitrogen, and that really kind of differentiates and determines what you're seeing. And so that also tells you the height of the aurora, or helps of the aurora. There's other ways to get a better confirmation of what height the aurora is happening at. But you can see how in our atmosphere, at different altitudes, different particles and molecules will kind of have a larger concentration. And so they're the ones who have the predominant impact from these particles from space. And so they then let out the aurora there. I suppose I should give a call out to Steve. I don't know if there's any Steve folks in the audience, but Steve is a new type of aurora that was actually discovered by citizen scientists. And they have a ton of really cool stuff online as well.
I forgot, I did hear about that.
Aurosaurus.
Yeah, also, I was gonna say, Chris, I totally Googled you and I found the Aurosaurus website. So that's like citizen science for auroras?
Yeah, it's basically a website where people can report that they've seen the aurora. I think usually they're doing it on Twitter now. So if you ever see the aurora and take a picture, tweet it and include Aurosaurus in your tweet, and you can let other people know that you can go out and see the aurora.
Also, that's a fantastic name. I feel like, is there Aurorasaurus? There should be a shop for one thing, and like swag of Aurora dinosaur for sure.
And I actually brought up I brought up the website there really quickly, the aurorasaurus.org. That's the correct website, right?
Yeah, that's the dinosaur.
I had no clue that was a thing. Wow.
Me either.
Cool.
And it's fantastic because going out and hunting for aurora in the dead of winter and it's so cold. I mean, if you can have confirmation that somebody else has seen it in your area, that is so nice, because then you can make sure to bring the right amount of hot chocolate for that evening's viewing.
Right. I know that's the thing about optical observing of any kind, is that the colder, the clearer it's likely to be.
Yeah.
So it's kind of like that trade-off. You get to look at some really cool stuff, but you have to freeze sometimes to do it.
Yeah, and the other great thing about this is that even if you don't live someplace where you can see the aurora, you can go on the Twitter and see all the photos that other people have shared to the Aurorasaurus.
Mm-hmm.
Oh yeah, that's kind of cool too. Is it just on the website now? Is there an iPhone app?
I think right now it's just on the website.
That's fair. And so now Earth is not the only planet that has aurora, right?
No. Yeah, any planet that has an atmosphere and has particles, charged particles that will be hitting it, can have the aurora. So we've seen the aurora on Venus and Mars, and I think we even have some telltale sounds of the aurora from, is it Saturn? Let me look at my
Yeah, I think it was Saturn that we had.
Yeah.
Yeah.
And so,
yeah. Happen.
Chris, do you want to describe the auroral kilometric radiation?
So basically what it is auroral kilometric radiation, or AKR, is a radio emission that's produced at the source of the aurora. And if we play the sound here, it's what you're hearing is basically the spacecraft picking up different sources as it orbits the planet, and the sources can be moving. And so when you convert the radio signals into an audio, you get these really spooky noises.
It's really bizarre sounding.
Yeah, I feel like this should be like the soundtrack in a haunted house.
Yeah.
Yeah, they are pretty spooky. And so this one was an example from Saturn that was taken by the Cassini mission. We also had an example of what the auroral kilometric radiation at Earth sounded like. If we could play that quick.
Yes, we can.
I couldn't quite read the one of the axes, but what's the frequency? Kilohertz?
Oh gosh, yeah, this one would be up in the high frequency range. And so these ones have actually been shifted down in frequency so we can hear them.
Okay, got it.
Yeah, that one was in kilohertz, it said.
Thank you.
And the other one's the AKR, right? That's the other one we're looking for?
Yeah.
All right, let's get the AKR up on the screen really quickly here. It's the first time I've done so many sounds on Virtual Astronomy Live. It's fantastic, though.
Whoops, you got the wrong one. There's the Cassini one again. We've got the Earth one.
Ah, you want the Earth AKR, is that correct?
Yeah.
Yeah, we want the Earth one this time.
Got it. Earth AKR. Whoa!
There we go. Because we have taking this measurement at the same time.
That's bonkers.
That's a much angrier sounding.
Yeah, yeah. It's angry. Aggressive.
Yeah. Yeah.
Go ahead.
Oh no, I was gonna say one of the things that's really cool is that with the aurora, we're still trying to learn what all the different processes are that generate it. And one of the things that is thought to cause the precipitation of those particles that ultimately end up creating those lights is chorus waves. And chorus waves are one of my favorite sounds from the magnetosphere, because when we first started going up into space, getting a lot of data was difficult, and really kind of processing and understanding that data. I mean, we barely had computers that we would consider, sufficient. Well, they wouldn't work for our phones. This was back in the day. And so we often would do things like listen to the data to be able to hear what it different events. And so one of the things that they found was, or what that we find now, is that people used to identify these different types of events by either the way they looked or their sounds. And the chorus waves were named after how they sound, because they often happen on the dawn side of the Earth, so on that morning side. If you think of the Earth and the sun as kind of, this was always really difficult for me as a student to understand. If you think of where you are around the Earth as a sundial, effectively. So if you're looking straight at the sun, that's noon. If you're looking behind you, that's midnight. And then on your right-hand side, I'm dyslexic, so I always have to double check. The right-hand side is dawn. And so these waves happen over there, and kind of like birds in the morning. And I didn't really understand that until I moved to Australia, where the birds are really, really loud. And sure enough, they sound like a dawn chorus of birds. So that's kind of a fun way of identifying different scientific kind of phenomena. So I don't know if we wanted to listen to the chorus waves. I believe it's called, well, there's chorus waves and particle bouncing. I don't know if that's the better one, Chris, or do you think that the radiation belts and better file to listen to?
We can do the chorus waves.
All right, I'm on it.
I love that they're named like that. That's the sound. The name of the sound is chorus.
Yeah, no, and this one's got the video that goes with it that shows the particles, the electrons and ions that are trapped in Earth's magnetosphere, and courses made by the electrons as they drift around the Earth and Earth's magnetic field, and they bounce and gyrate around. That's how these waves are generated.
Are we getting audio on that one? I'm not getting audio on this one.
It looks cool.
Yeah, it does look cool. But I don't actually have audio in this one, it looks like. That's weird.
Oh, no. Well, we can listen to the other one then.
That answers that then, yeah. Unless there's some...
You just make the chorus waves with your mouth, right?
Oh, I wish.
Yeah, it's acting like it doesn't want to put the audio out. So let's hop over to the other one, the radiation belts and chorus. And there's a lot in there.
So in the image though, that the extended disc, is that the edge of that supposed to be the radiation belts, or are the radiation belts contained inside that?
Yeah, it's kind of that region. You can see where they try to highlight, so it gets the more opaque. Yeah, opacity. It has a larger opacity, where there's a larger density of particles there. So space is massive, and these particles, even though it's more dense there, are still not really colliding with each other at all. It's a very, very long mean free path. So all that means is that it takes a very long time to run into another particle. It's like living out in the middle of nowhere, Montana. You're not going to run into another person for a while.
I found it.
There we go.
There were 2 buttons to click.
That sounds like the birds, for sure. I kind of half expect David Attenborough to be narrating it.
Yeah. Oh, that would be so cool.
I think that needs to happen.
Yeah, and there's lots and lots of different types of chorus waves, and so I think we also have the giraffes.
Yeah, we have the giraffes in space, which
I love that plot.
they gave it that name because of when we made a graph of the data. It looked like giraffes roaming across the savannah. And what this really is well, we've had a couple of these now. They're a spectrogram of a waveform. And what the spectrogram shows is if you start at the bottom going up on each graph here, it shows like it starts at lower tones and it goes up to higher frequency. There we go. We've got the giraffe.
I got a giraffe in there for us. Nice.
And then time marches on left, from the left to the right. And when we play this one's a really cool one because every spacecraft has multiple antennas on it, because one of the things that we need to know when we study these waves is how they propagate, like how they're polarized and what direction they're coming from. And so we make 3 measurements that are all perpendicular to one another. And so this one has a stereo effect made by one spacecraft by taking each antenna and putting it into a different channel in the audio.
Let's see how this goes.
Kind of like the right-hand rule.
Yeah, exactly.
Like the upswing starts to sound like the Star Trek.
Yeah. Yeah.
So another thing that's kind of neat about this one is there, you notice there's sort of that low sort of roar in the background on this. And if you look at the picture here, you can see that the giraffes are poking their head up out of this sort of bright area. And that bright area is something called, another wave called hiss. And actually hiss and chorus are related. And we don't really understand how they're related because, yeah, it's right there. There's the hiss, and then the chorus is the giraffes coming up out of it. And that's one of the things that scientists are trying to understand, because they're actually both what we call the same wave mode, but they look completely different. And they interact with the particles in different ways too.
Yeah, and so we think that one of the ways that they might be related is that the chorus waves live kind of in the radiation belts and outside of the plasmasphere. The plasmasphere is this really cold region of space. There's lots, it's just kind of lots of heavy, slow particles. Again, it's still so big, space is so big that these particles still don't collide very often, but it's more dense than the radiation belts. And we think is that the chorus waves might be actually coming from outside of the plasmasphere into the plasmasphere, and then that is what ends up causing it to become kind of all mumbled and jumbled together. And so they're a little bit more angry and hiss-like then, right? Instead of being nice and free out in the radiation belts. But
and then just to like big picture, even bigger picture, all these particles, are they kind of hitting Earth and hitting these, coming into these magnetic fields because of the solar wind? Or is that what's sort of initiating any big action?
Yeah, some of them definitely are. And then you have some that are actually coming out of our atmosphere as they get heated up and ionized from the sun. And so they then get trapped and come out. So you have a combination of both these particles that at one point in time came from the sun and the solar wind, and then other particles that are actually coming from our Earth's atmosphere. And that's kind of a cool thing. Yeah.
And since these particles they're electrons and ions, we call it a plasma, which is, it's sort of like a gas, except everything that's in this gas has an electrical charge. And so it interacts with the electric and magnetic fields in the space surrounding our planet.
Okay, got it. And just to go back to the ITM,
yeah,
can you specify the differences between those 3 things, or at least like when you're talking about the the magnetosphere, the ionosphere. What other spheres are we talking about?
Oh, we have so many spheres and so many different spheres that everyone lives in. And so it's really kind of fun because in the actual world, there is no barrier between any of these regions of space, right? And so you have the atmosphere that we live and breathe in now, right? You have the kind of a slightly higher version of the atmosphere where we fly planes, and then a higher version, which is into the stratosphere, where you have balloons that can go up really high. And then you have the mesosphere and the thermosphere and the ionosphere, and all of that starts kind of coming together, and they move and shift. So as the sun heats up our atmosphere, it can expand, and all of these regions then kind of expand with it. And then that goes out into the magnetosphere. And the magnetosphere is really just kind of the region of the universe where our Earth's magnetic field is the magnetic field. So that can go throughout all of these different regions. And then you have the heliosphere, which is where the sun's magnetic fields are dominant. And then you have the galactic, I don't know what we call that actually. Is it the galactic sphere, the Milky Way sphere? I don't know. But you can go out and out and out. And so it's just kind of what's the dominant influence there. So in the ionosphere, that's where you start having collisions of these particles. And so we tend to think of the magnetosphere, you don't have to worry about collisions between the different particle populations. And then in the ionosphere, you start maybe having to deal with that. And as you get into the atmosphere, everything's collisional. And so you start having different types of physics and different types of chemistry that are more important than others when you're trying to model and understand it. I hope that helps explain it a little bit.
It does, and it makes it sound really cool.
It is really fun.
And of course, the waves that we've been showing, come from different regions in this whole system here. And like when we were showing the aurora are generated in what the layer that we would call the ionosphere mostly.
Okay. So you just said though, Alexa, about the layers kind of, they heat up, they puff and stuff like that with incoming heat or energy. Is it noticeable? Is there a cyclical nature to it with just like the side that's facing the sun? It was kind of just a rise for that part of the atmosphere that's always facing.
In fact, we saw some really cool waves that were generated from the solar eclipse. So the solar eclipse came and effectively it was the moon putting a shadow over the Earth, right? And so when the solar eclipse happened across the US back in 2017, we had tons of people studying and measuring these things. And they actually saw the atmosphere create this wave because of this shadow cooling down a little path of atmosphere on the day side. And so that's really kind of fun, right? Is that our atmosphere is always responding to these different kinds of influences and temperatures. So you get,
I remember watching the eclipse and feeling the temperature drop.
Yeah.
It was 80 and then it plummeted and I put a sweater on and it was wild.
Yeah, it is absolutely crazy. I have never seen an eclipse in totality, which I've been told is like the best thing ever to watch. So I'm really hoping, I think it's next year, it's going to be crossing again, I think. We should
2023 is an annular and 2024 is the next North America total.
21, that's right, is in Antarctica and South America. Yes. And so we're hoping that, in 2023, I can get like a hotel in, I can't remember, somewhere in Vermont, there's going to be a total solar eclipse. And that seems like a really nice place to kind of hopefully have few enough people that you can get a good spot and still be able to see all of totality. So we'll see.
Although it's April, so it also could be snowing.
That's true. That is true. But there might be fewer people then. And it'll probably be warmer than most of the times I had to go watch the aurora. So,
There will be fireplaces.
Yes.
Yeah. Okay. But are those the waves, some of the waves that were happening or observed during the solar eclipse? I remember there were a lot of people saying that you could see something, like normal people could see some sort of texture in the shadow or like a certain type of structure. And I have no idea if that's related to what you're talking about or not. So
not if I'm thinking of the same thing that you're talking about, then I don't think so. So when you had the sun kind of before it became fully in totality, it creates really cool shadows through the leaves. And so you never want to look at the sun straight on.
Okay, yeah, this is different than the little ellipses through the trees.
Oh, okay.
Is that what you were talking about?
Yeah, so the things through the trees, yeah, you can see it going through there. And so that's a safe way to observe the total solar eclipse starting to come into view. And so you can not look at the sun, but look and see the eclipse and the shadows coming in through any sort of like little pinprick. And the leaves are really a fun one to look at it through, because it just makes all these weird, cool patterns.
They are super cool. Okay, yeah. So we're getting away from sound. Sorry about that.
It's still waves. It's all waves.
That's true. Speaking of another one of those other spheres, though, like the heliosphere, I think that we also have some stuff related to Voyager.
Yeah.
Yeah. So maybe with this, though, what we should do is we should start out and look at the type 3 solar radio bursts. So because actually it's related to how we know where the heliopause is, or boundary of our solar system. So what happens is when you have like a solar flare on the sun, and these often have like a coronal mass ejection. People have probably heard about these too. When one of these solar flares, it sends out energetic particles streaming out from the sun into space. And those particles can make a wave called a type 3 radio burst. And that can make a really cool sound.
So I've got a couple different things in here. I've got arrives at Cassini. I've got CME and particle blizzard. Which one do you want to start with?
How about the CME particle blizzard?
Yeah, let's show the CME and particle blizzard. So that'll show where it starts out, and give you an idea of what's making it. We'll start at the sun. So there's the CME, and that snow that you see is actually all these particles impacting on the imager. This is from the SOHO spacecraft, and it looks like this snow here. And this is an image of the coronal mass ejection. And the reason why there's like that funny circle in the middle, that's called a coronagraph, because you can't image the sun's corona unless you block out the sun. You can also see it when we were just talking about eclipses. We could also see the corona during an eclipse too.
I used to spend a lot of time on the SOHO website looking at the videos that they would record, because it was just so cool to look out for these kind of the magnetic loops, and then sometimes definitely the coronal mass ejections.
Yeah, and so all that noise is actually saturating the camera, and that's part of the reason if you didn't have that cover there, the whole camera would be saturated by the sun. So it's also not good for a lot of our instruments to look directly at the sun either, you know.
Exactly.
Yeah, and we also have, I think there's a radio burst flare movie, if you want to bring that one up. That one should show the actual flare itself. So that bright flash is the flare, and once again you can see the particles coming and hitting the detector. This is a really zoomed in view. This is also from another instrument on the Solar Heliospheric Observatory spacecraft called SOHO. And so when these particles go out into space, they make this type 3 solar radio burst, and that we have the sound for when one arrives at the Cassini mission, which is actually a mission to see Saturn, but these things propagate all the way out through the entire heliosphere. And so, you know, if you're in the right spot. And so here we go. So we have another one of these spectrogram things. And so what's happening here is, whoops,
it went back to the wrong one. Yeah, here we go.
There we go. Is you see that 69 minutes?
Yeah.
That's how long it took to get to the sun, from the sun to where Cassini was. And that whoosh sound that you hear sweeping down in frequency is because the characteristic frequency of the plasma in the heliosphere is changing as you go out further from the sun. And so the frequency of these waves changes too. Yeah. So these things can keep going all the way through the interplanetary space. And what happens if when you get out, close to the heliopause is that these disturbances can reflect off of that boundary. And so now if we bring up the Voyager one.
And so what's like the definition of the heliopause? Like, is it it's a pause between the...
So it's kind of like when we were just talking about the magnetospheres being the region where Earth's magnetic field was kind of controlling everything.
Yeah.
The heliosphere would be the region where our sun and the solar wind and the sun's magnetic field would be controlling everything. And so you see in this drawing here, you know, it shows Voyager, and it has the heliopause, and it has the sun sort of right there in the middle, the teeny tiny thing, because the heliosphere is huge. And so this would be the boundary, this heliopause would be the boundary between where the sun and the solar wind and the sun's magnetic field are dominant versus the interstellar medium that's in between our solar system and the other stars.
Yeah.
And so, so this illustrates what's happening here is, so when these disturbances, these shock waves coming out from the sun, from the CMEs, and solar flares get all the way out to this outer boundary, they sort of interact with this boundary and produce radio emissions. And that's actually what the Voyager spacecraft was detecting, is when these disturbances go out and interact with that boundary. And it can take a year or more for one of these disturbances to make it all the way from the sun out to the heliopause. And so if we want to play, we had the audio, the heliopause radio source audio, we can listen to that.
Wow.
Yeah, it's kind of loud. And now you can see on here that the time on the bottom is in years. And so these are, we're hearing years of data. It's all compressed down into a short time so we can hear it. And many different disturbances making their way out and then interacting with the heliopause and producing this radio emission that Voyager detects. Here we have another one. Here coming up on one little one at the end.
Now, Chris, these all happened every 10 years, it seems like, or thereabouts, and it's very similar to the time frame when we have solar maximums. Is that why we see more noise during those times? Do you know?
Yeah, I would say that that's what it is. I mean, we have more when the sun goes through its cycle here. There's a period called solar maximum, and we see more activity on the sun, more solar flares, and more coronal mass ejections, and then of course more geomagnetic storms and aurora on Earth and the other planets that have magnetic fields. And so that's why you're seeing this every, you know, this kind of regular pattern here, is because the sun is more active and you're seeing more disturbances. And, you know, and it's just, I think one of the neat things here is that this is, you know, an example of some of the other ones that we showed, like the course waves. The spacecraft was measuring things right there where they were happening. But this one, we're kind of using the radio waves to remotely sense what's happening just upstream from us.
Right, because I mean, I don't know the answer to this, so I'm not sure if either of you do, but did Voyager, when they launched Voyager, did they know or expect that there were measurements like these that they would be able to get out of its data? Or is it kind of just more, they find more and more creative ways to tell something about Voyager's environment based on what we did launch it with?
You know, I think it's a little bit of both. I mean, I think, you know, the interesting thing about Voyager is because it's been traveling for so long, the technology and our understanding over the course of its long journey, you know, has evolved. And so when Voyager was launched, we had a certain idea of how the planets were and how our solar system worked. And as we gained more and more knowledge, not just from Voyager, but from other spacecraft orbiting the Earth or visiting the other planets, as Voyager was continuing on this journey, we changed what we were looking for and what the objective of this mission was.
Right.
I don't know if we even expected that it would last this long. I mean, I think this is a huge accomplishment for everyone back in the 1960s and 70s who first conceptualized the idea and then built and launched these spacecraft. The fact that they're still working and we're still hearing from them is really astounding. And one can only hope that you're going to have an impact like that on the field and on humanity, because this is literally the first things coming from Earth that are going out well beyond our solar system, that are going to forever be kind of traveling through our universe, which is really quite powerful. I can't even talk this. It's so cool.
I know, right? Okay, but so going back to the Voyager 1 and the heliopause, for anybody, I don't know if you guys read XKCD, but there's like a running joke about how many times Voyager has left the solar system. Yeah. Because it was this whole issue of like, oh, we think it has now because of this measurement. And then there was more measurement and it's like, no, this one. I don't know, Das, if you saw my chat, if you can pull up that website just for kicks.
Which one was it?
I sent you in the chat a link of the XKCD comic that is keeping track of the number of times, like basically the number of times the press probably pounced on a scientific result that they blew up to say it left the solar system.
Wow, I don't know if I've seen that one, but it is kind of, since I work with people who built the plasma wave instrument on Voyager and who have been, analyzing the data throughout its mission, it's kind of a running joke at work too, like how many times it's crossed it. But that brings up another interesting thing. Is that these things are dynamic regions. It's not like a hard boundary that stays put where it is. Depending on the activity from the sun and what's happening outside, like this boundary can move.
Right.
And so it is kind of a moving target, just like when we were talking about where the layers of the atmosphere are and how those can kind of change and evolve between day and night. And actually those even change with solar activity too. When we have a solar flare on the sun or CME on the sun, the shock wave that comes out can actually compress Earth's magnetic field, and it produces a storm, and it can interact in a very similar way with the other planets that have magnetic fields. And so there's all these we talk about all these boundaries in space, but they're not boundaries in the same way that you would think of the boundary between like the US and Canada or something like that. It's not like a hard boundary. It's it's like variable
or something.
Well, they move, right? So they have these things. In fact, I have my lithave magnetosphere here.
You got
it. And so these field lines, they do tend to kind of come back and forth. And so it can, have a little satellite sitting right here. Mm-hmm. This boundary might move across it. And so while it's moving, right, this boundary is going too. And so it's a really neat thing that I think we're still trying to learn about. I mean, space, as I keep saying, is huge. And we now have 2 data points way, way out at the farthest reaches of it. So just trying to understand what the shape of all of this looks like is incredibly difficult. And understanding the dynamics of how it's moving and how it's breathing itself is really, fascinating to learn. And the more satellites that go out there and the more we're able to study and get data points of this, the better we're going to be able to understand it. So, I have a feeling we'll see it cross a number of times again.
As I did find this. This is what you were looking for, right?
Yeah.
Very nice.
Very good. But yeah, I remember, I think it was maybe 2007, based on where I was living at the time, when there was a report that the solar system was dented. But I think it was because Voyager 1 went one way and Voyager 2 went another way, and the two different extents of what they measured as where that zone sort of ended, the sun's zone and the interstellar one were different distances. So it wasn't like a, proper spherical radius. It was like different radii. And so, yeah, the press interpretation was the solar system was dented, but.
Yeah, it's never smooth. Nature is never quite ideal and perfect. And so you get these weird dents and bubbles and things. And that's some of the fun things to study. I mean, it's where the really interesting stuff happens. What caused that dent? Why is there that difference between them?
Yeah. And I would imagine that because of the sun having a magnetic field, just like you were talking about the Earth's one, the sun has a burst and it can get kind of squished. The sun is moving through the galaxy and it's passing or being passed by other stars, in addition to whatever combined magnetic field is between all of the stars. So I would assume that its motion maybe is making it permanently not spherical because it's kind of heading through something.
So that's exactly what happens with our Earth. And so the Earth, normally, if you look at just the blue ones here, they're as symmetrical as I can make them. I am definitely not an artist or a good crafter, but they're about as perfect as you can get when it comes to being symmetric across the entire world. And then you have the ones going further out that are more and more distorted. And that's because the sun's magnetic field and solar wind is coming and it's compressing this side. And then it's lengthening out this side. And so the interstellar, sorry, I'll get these right, winds, I believe, are not quite as harsh as our solar wind is to our magnetosphere. But you have the same thing. You have them coming up and buffing them. And then you have the sun moving, like you said, through the whole system too. So you have a relative velocity there. And so you can get these weird shapes and dents happening. It's all these pressure balances. Where can they hit and collide, and where is it going to be here today and maybe there tomorrow, kind of thing, so it's really fun to see. Yeah,
Chris, did you want to add anything?
Oh yeah, I was just going to say that we had, as we're all have all these magnetospheres, Jupiter's magnetosphere is huge. Because Jupiter is it's a big planet, and it has a huge magnetic field, and Jupiter's magnetotail, this region that Alexa was talking about, where the solar wind sort of drags out the magnetic fields, Jupiter's magnetotail can go all the way to Saturn.
But then you have inside Jupiter a moon that has its own magnetic field that is quite small. And so that's Ganymede, which is
We have a file for listening to Ganymede.
We do.
Yeah, we do. So there's a picture of Ganymede, and we have some radio sounds that were made by now I can't remember which spacecraft it was, Galileo when it was studying Jupiter. And actually these radio waves are how people realized at first that Ganymede had its own magnetic field and its own magnetosphere. And so there you have a magnetosphere and a magnetosphere inside the heliosphere.
Is it sad that I thought Magnifico when you said Galileo twice? Okay, I'll be quiet. Sorry about that. That was louder than I expected.
It's chaotic.
Oh yeah, and that's another thing is that Jupiter's very, very loud.
Wow.
And of course, this has been compressed and shifted in frequency so we can hear it.
I love these.
Wow.
So one of the things about Jupiter is that it is a huge radio source. And people talk about like, looking for signals from other solar systems. But if someone was looking at our solar system from outside, what they probably would hear would be, and the radio signals would be Jupiter, because it's just this huge radio source, and that's why it's so loud, even in this audio here.
In fact, we knew that Jupiter had radiation belts and had all of this stuff going on inside of it before we even knew Earth had its radiation belts, because Jupiter is just that loud and Earth is relatively quiet.
Yeah, it's like you know more about your neighbor than yourself.
Yeah.
Oh my gosh, that's bonkers.
It's yeah.
Yeah, and so this was Galileo. Yeah, so this is back in the 90s then, for this recording. That's like 96, I think, isn't that when Cassini actually launched, I feel like.
Oh my gosh, I don't remember anymore. It's so hard to keep track. Time goes by so fast.
It doesn't matter. What sounds haven't we listened to yet?
We've stuck within our own solar system. Did we want to try going out further to with Chandra?
Yes.
The sonification file?
Yes, these are really kind of fun. And definitely, I should preface all of this. I am not an astrophysicist. I'm not sure that I understand all of it, but it is really cool and really fun to listen to.
And it's different than the files we've been listening to now, because this one is like constructed.
Yeah.
Yeah, because so far what we've been playing back are electric and magnetic signals. So basically radio waves, like turning on your radio and listening to the radio, except these are instead of the man-made radio waves, these are waves that are being produced by the plasmas out in space. And these ones are they're taking images and turn them into data. I think Alexa can explain a little bit about that.
I think, Summer, you're actually friends with some of the people who do this, right?
I did pull it up if you want to explain it.
Sure.
So essentially what it's doing, so this is a multi-wavelength image. So it's got X-ray data from Chandra, optical data from Hubble, infrared data from Spitzer. And then what they did was they gave different sounds to each wavelength. And the sound represents the position and brightness of the source. So a louder sound, let me see, I think it says something about the higher pitch is the top. So from the top to the bottom of the image too, it's higher pitches at the top and lower at the bottom. And then for the intensity is the volume of the sound. So it'll be louder, the more light that type of wavelength is coming from that section. So this is an image of the galactic center. So looking towards the supermassive black hole in the center of our galaxy.
All right, you all ready for this one?
We're ready.
Let's see here. Hey, where'd my little plaything went away?
All right, that one disappears and then...
It's gone.
Oh no!
Let me go to the other slide and maybe go back real quick. Oh yeah, that fixed it. I had to go there and we just restarted. All right.
Less aggressive.
Nice and peaceful and meditative.
Very calming and peaceful after listening to Ganymede.
It's funny because I would imagine physically speaking that I'm yeah, so it had so the Hubble, basically the multi-wavelength is awesome because it can show you all different types of activity that you wouldn't see if you were only looking with the one wavelength. So the Hubble is showing you regions where gas and dust are and stars are being born. And then the Spitzer is much more larger dust complexes. And then the X-rays from Chandra are the superheated gases from both stars exploding and energy outflowing from the supermassive black hole in the center.
It's crazy how much you can see and learn from just one image. All of that is in that data that we were listening to and seeing. It's crazy. But yeah, it's really neat.
I think it's wild how we are stuck on this little rock, right? But we can't go there. So it's not like geologists where we can go to our field site or something like that. But but you can still like piece together all of these fascinating things just because we understand the physics and we understand the math. And so you can do all the like calculations here on Earth, but that explain what's happening way out there.
Yeah, and how each of the different wavelengths, so whether it's that you're looking at the different X-ray wavelengths or you're listening to different sounds and different pitches, you're able to hear the whole thing come together as you combine more and more kind of layers in there. It's really quite neat.
You're reminding me that, a long time ago, I went to a conference where I met someone who had sonified data from Mars, and I think from the atmosphere. And it was 4 different, maybe molecules that were assigned different instruments. But essentially what you could do is you could listen to the seasonal change on Mars, because it would change the density of them from the equator to the poles. And then based on, where it was in its orbit, it was just fascinating. It was really cool.
There was an experiment called, I think it was Crater, or was it Laddie, that went to the moon, where they actually then took the particles that were hitting the lunar surface and they gave the different, I think it was the different molecules got different instruments, and then their pitch or tone was the energy of them, and you could listen to, and that was really kind of fun. They had their own SoundCloud, I can't remember if it's SoundCloud account or something like that. And a lot of these, NASA has a SoundCloud account that you can go and listen to a ton of these on, and they have other things too, other audio bits, just interviews and things like that, which are also fantastic ways to learn about the world around you as well.
Yeah. Oh, sorry.
No, I was just saying I like SoundCloud with NASA.
Yeah, I was just going to say that one of the problems in the space sciences is how to visualize and represent your data. I mean, and it's really easy when you look at, images, whether they're ultraviolet or the visual part of the spectrum. People know how to relate to the images that are taken by Hubble or other telescopes, but it's really hard for people to relate to some of these other data sets, like what Alexa was saying, the particles bouncing, or these information about the atmosphere of Mars. And so that's one of the things that's doing that these sonifications can help is helping us relate to the data using our other senses, because sometimes just looking at a bunch of squiggly lines on a piece of paper is not very helpful.
No, that's such a good point. And there's patterns probably that sometimes different people's senses might pick up on better than, like you're saying, like looking at a graph. But maybe you can hear the differences much better than you can sort of arbitrarily say, like, yes, this peak is higher than this peak, or these are 2 separate peaks.
And we use a lot of similar techniques for looking at these kinds of data as people who mix music and who work in the audio world all the time. This all processing waveforms, and so we use very similar analysis types, and I think there's a lot we can learn from each other, from looking across at how other people have started putting data together and started looking at things. Cleaning up noise is a huge issue in a lot of these. I mean, removing different bits of Jupiter so you could hear Ganymede, I'm sure, is a monumental task, just because Jupiter's so loud. But that's part of the things you do, is you try to remove the signals about, so you can find the other little blips in there and figure out what was that little chirpy noise you heard, at 2 minutes 40 in the clip that you're listening to. It's really kind of interesting how we try to process all of this together and find those little golden nuggets. But
yeah, you make me wonder if like Hollywood might have a lot of experience with like the, fixing the noise, so to speak, on mics, because also they have bigger budgets sometimes than science does. So I don't know if you remember the black hole in Interstellar. It was computer simulated, but it really only happened because they actually had Hollywood money to do it, even though it was still being done by physicists at Caltech. But they never would have been able to do that on their own research grants.
Research grants are quite small. That is true. You're not going to make a Hollywood movie after that, on one of those.
Yeah. Okay, so as always, we can usually talk forever about all of this really cool stuff. But we filled the hour. And so now it's time to give some question and answer time, because I'm sure there's a million questions that I haven't asked that other people want to hear the answers to. So Das, you've been collecting some of those?
I have it. It always happens. People are like, "Oh my gosh, how are we going to talk about that for an hour?" And then we get to the end of an hour, and we're like, "We could keep going forever." It's such a fantastic ability to be able to just sit here and talk about this stuff. A ton of people. I'll tell you, the number one question we've got is where can people find more sounds like this, websites to go to. We've already linked up the NASA SoundCloud that was in here. jpl.nasa.gov had a bunch. The moderators were looking for some more links for things like that. And for the Chandra sonification, I actually took that out of the PowerPoint slide and I pasted it into chat because people want to listen to more sounds like this. Are there?
We need to make sure. I mean, Christy, you're part of the Iowa SoundCloud group. And that's, they have a ton of sounds there from all across the heliosphere. Every single planet, I think, has, or maybe not every single one. I don't remember.
Yeah.
We may have lost the audio
there. And they have a Twitter account too.
Yeah, we'll see if we can
audio.
Find that. We might have lost Chris there for a
Yeah,
second.
there's
there we go. You're back.
Yay.
Yeah, my internet connection is acting up here a little.
Yeah, just a little bit there. We're getting a little.
What was I going to say? If you go and you look at there's a YouTube channel, this audio, and that has a lot of the sounds with the little videos like we've been showing from the various instruments that have been built at the University of Iowa. And if you also go and look at the website for the physics department, the Department of Physics and Astronomy at the University of Iowa, for in the radio and plasma waves group, that there are also a lot of sounds available there.
The University of Iowa Physics Department?
Mm-hmm.
I'm literally Googling this right now. Like,
let's see.
We've got Iowa Physics, Department of Physics. Was there like a sub-department or something we should link them to, or?
If you go under research, let's see if I can put it in here. If you go under research groups, there, I think if I have the right.
And I'm wondering if trying to bring up the web pages is causing your video to hiccup a little bit there. Because it looks like you're doing something and then it sort of breaks up the video just a bit. That may be what's going on. No big deal at all, though. Totally not a big deal.
Okay, I can't type it in the chat. Then maybe it'll be a little funny. But yeah, and the group at the University of Iowa has actually worked with some artists before to produce musical compositions using some of the sounds from space. So
gotcha.
It's pretty cool.
Yeah. So
yeah, and for the Chandra, I just want to give a shout out that they also did 2 other sources in space. So they did the Cassiopeia A supernova remnant, and then the famous like pillars of creation as a really famous Hubble image. And so they sonified both of those too.
So we'll turn the mods loose. The chat moderators over here trying to get another couple links. If y'all find anything like that, maybe we've already linked up this one, the Chandra sonification. If we find anything else like the Pillars of Creation or anything like that, mods, if y'all just link those up into chat here. And I will ask after the show. We always have the website that has, you can go back and watch the VOD, and I'll see if we can't maybe take all of the links out of these out of the PowerPoints and put them there on the website so that people can go back and click through them directly, and then by going to that website, chandra.sa.edu, over to here, you'll probably branch out down sort of a Wikipedia-style rabbit hole where you find more and more things on those websites by going to them. So that... I
mean, you'll be able to, you can find Sputnik, you can hear the first sounds in space, you can hear Philae landing on the asteroid, or on the moon. I can't remember if it was an asteroid or a moon. Yeah. And so you can hear those sounds, and those are the Philae one. That's a real sound in space. That is an actual audio, which is really kind of cool too.
I think I've got it here. Let's see if I can play that one back.
There's so many sounds out there.
Here we go. Let's see what it sounds like. There you go.
Confirmation.
So
it's like a nice when you slam the car door. It has that nice thud.
It has a
Now,
nice.
was that the actual landing, or was that the initial bump and then it floated again? Now?
I can't remember now.
I just
think
linked
you're
up in
right.
chat the link from the PowerPoint there.
Yeah,
Yeah.
that's from ESA. And I believe they have a really nice blog description of it, but I can't remember now off the top of my head if that was the bounce or if that was the actual landing.
Yeah, it's sensors in the feet of Rosetta's lander Philae have recorded the sound of touchdown as it first came into contact with the comet. So that was the first, initial, I guess we call it the bounce, right? This is an actual sound file, right?
Yeah.
The bounce, the ricochet, whatever Philae did there. Yes. So I'm going to go through, and I've got some other questions here because y'all have been asking some really great questions throughout the course of the show. And let's see what I have in the queue here. Let's pop over this way. There's that. So let's see. Oh, I have to ask this question. You know why I have to ask this question? Because my mom is watching and asked the question. So my mom has a question for y'all. And this is about the International Space Station and sort of how all this ties together. We've heard all of these sounds in sort of sonifications, like we're listening to this stuff, but is it really a sound? Do astronauts on the ISS hear anything like this, or do we know of anything like where this radiation affects their instrument, like they're talking to Houston or whatever, and they go, they hear something on there? Do these sorts of things affect the astronauts on the ISS at all?
So these sounds, that they're not going to hear them. This is well above what we can listen to. But this radiation can affect astronauts. So if you remember the solar storm where we saw the video with the sun and all of the big white snow kind of coming in,
Yeah.
that stuff is actually hazardous to astronauts and also to our equipment. Comes to communications for the astronauts, space weather. Chris was talking there earlier when you were giving your introduction. Some of these effects can actually cause disturbances in our communication systems by changing the atmosphere. So sometimes all you need to do is to change your frequency. When we have these communications with radar or radio, you typically bounce the ionosphere.
Yep.
And so if the ionosphere has moved, if it's gone up or down, then you end up wanting to change your frequency so that you can still match the ionosphere and get the reflection back down to where you want to go.
Gotcha.
So there's easy fixes, but it does still have an impact.
Right.
What Alexa's just describing is something that we call a solar radio blackout. And because it effectively blacks out communications over a portion of the Earth that's affected by this event.
Gotcha.
But when you have a big blackout, you actually can't reflect over the horizon. And so that's when, if you're, say, trying to make sure to communicate with someone, if there's a hurricane or something like that, instead of trying to bounce over, then you might need to use line of sight. So you might need to have relay, something like that. But it's not something we want to know about, so you know that's why you can't talk to somebody,
right? And
you know then how to fix it, but it's maybe not a huge catastrophe. It's not a big deal. Yeah.
Gotcha. Which the one where we had the center and you saw all the particles sort of come at the camera? Which file was that? I wanted to bring that up really quickly.
That was the Type 3 radio burst.
Type 3 radio burst. Okay.
Yeah, that was probably the particle blizzard one.
Yeah, let me see if I can put that on the screen really quickly. Okay, here's this one, right? Where was this taken from? Like what instrument recorded this? Where was it?
This is SOHO, so it's sitting in between the sun and the Earth.
Okay.
And so when we see these things coming at SOHO, we have about a 40-minute warning, more or less, that there's been a big event on the sun and that we need to let the astronauts know that they should take cover and just be protected.
Gotcha.
You know?
So this is what I wanted to point out with this image, right? And I'm going to keep sort of looping it here. But this is the instrument on the spacecraft that's a little bit closer to the sun than we are, right? So we get a little bit of warning, like you were saying, right? But look at this. It goes from the beginning where it's all nice and clear, and then you get this big storm all of a sudden, right? Well, this is hitting the sensor on the spacecraft, but these same sorts of particles would be going through the International Space. They'd be hitting the ISS. They'd be going through the astronauts. They'd be going through whatever's in the way. That's sort of how they work if they're on the side where these particles can get to you. Am I saying this correctly?
Yeah, it's one of the things that we're definitely trying to learn how to predict and how to mitigate. So we want to make sure that we know how much shielding do you need to put on a space shuttle. So when we send to the moon, they're protected as well. Because right now, the International Space Station are inside of our magnetosphere.
Right.
And our magnetosphere can help protect and block out a lot of those particles. Not all of them, but a good chunk of them. And so that's definitely studying and trying to learn more about, so we can make sure to keep the astronauts safe.
Gotcha. So for that, the Earth almost has a natural electromagnetic shield around it that protects people that are inside the shield from a lot of these particles, right? And once you go past it, once you go past the Van Allen belts, like we did with Apollo, humans going out to the moon, or SOHO here when we send spacecraft out beyond the immediate orbit of the Earth, I guess, they're going to go outside the magnetic shield that Earth just conveniently has here for us, and that's when we have to start dealing with this. I'm paraphrasing all this. I hope I'm getting close enough to the explanation, right?
I think you're doing a fine job.
Okay, cool. Thank you. I have a stamp of approval there. So let me grab some more questions here, and I promise the rest of them, it's not just an entire question queue of questions my mom has asked. That one was first in the queue, though. I didn't stack that or anything.
We're happy to answer those offline too from her.
Excellent. So this one was really interesting, and it was from a user who said it was an interesting idea to visualize these signals with audio. Do you know of any of these kinds of representations that can be helpful for blind people or visually impaired people that are learning science? And almost sort of my follow-up to that, have you ever learned anything by shutting down your normal senses that you're looking at it? Like, oh yeah, I'm looking at this data or something, and I'm just going to close my eyes and I'm going to listen to the sonification, and you hear something that maybe didn't really stick out before, or some sort of pattern comes across. Is that a thing? Is that possible?
Yeah, I can't remember who wrote the paper, but many years ago, I remember reading a paper where a scientist had basically used listen an audio to identify when there was chorus, that he listened to the signals to pick out the times when there was chorus rather than sorting through piles and piles of spectrograms. And then some things in my own work, we showed today these chorus waves, which have these little chirpy rising tones that are made by electrons mostly interacting with Earth's magnetic field, but ions can do the same thing. And so I'm looking at some very low frequency waves, but sometimes it's hard when you're showing people these spectrograms to get them to see the thing. So, and understand what you're talking about, even when you're standing right there pointing at it. And it really helped that at the last conference that I was able to go to in person, I had audios and we all listened to the audios, and then you could really, hear this. And even for people who knew that they were there, it was really exciting. It was like, oh my gosh, I can hear these things and in a new way. So yeah, I mean, you can use these, to look or to learn about the data in new ways. So
that's really cool.
No, I think it's, anytime you look at the data format, whether it's plotting it differently, listening to it instead of visualizing, I think it's fantastic, because you're always going to pick up on new things. You're always going to see it in a slightly different way. And even if it's not the final thing, it might lead you to a new thing, a new way of visualizing it or listening to it or thinking about it. So you get that whole picture together. And then anytime we can make science more accessible to everyone, I think is a good thing. And just on that alone, it's a reason to make sure we continue to do this.
Yeah, absolutely. I mean, taking this something that may just be, what is this? It's just a bunch of numbers. What am I supposed to do this? And then turning it into images so we can visualize it, turning it into sound so we can hear it, and just making it more accessible to all sorts of different people who perceive things different ways. It's a fantastic thing to do. That was a really great question that I wanted to get in there. Over and over again in the question queue, it's, is there a website I can get to these space recordings? How do I find more space recordings? I gotta have. Apparently, we've let people know that these things are out there, and they just can't get enough of these space recordings now. So we've done our job tonight. That's fantastic. This was another good one, and I think I sort of know a little bit about the answer here. But Xbox Bro asked, "How have the noises coming off Earth changed due to changes in our atmosphere?" So that's sort of like a climate thing, maybe an atmospheric thing. And then we were talking a little bit earlier about the electromagnetic environment, right? So while we may have some climate change stuff going on affecting Earth's atmosphere, which is sort of where the question was going, are we affecting the electromagnetic shield, like I was talking about, around the Earth with what we do down here, like all of our radio emissions or anything like that? Can we change the electromagnetic sphere?
We sort of do. I don't know if I'm going to quite answer the question the way it was asked. So let me know if you want some if I'm not quite getting there. We do send out electromagnetic waves into space. In fact, we can see impact on the radiation belts themselves and the particles that are there. So we had HARP, which is a fantastic instrument up in Alaska, which generates these waves. So we can generate the coarse waves and the emic waves, the electromagnetic ion cyclotron waves, and see how they affect the particle population out there. And that's really important for us to be able to do, because when we're living in, and when nature is our laboratory, we can't control all the variables. We can't tell the sun, I want you to make me a storm like this today, and I want the magnetosphere to look like this, know exactly what's happened. Instead, we just have to look at many events and try to figure out exactly how they work together. What's cause and what's effect?
Right.
Are these two things happening together because this one causes that one? Or is it because there's this third thing that causes both of those? And so these two aren't necessarily fully related. They're related because of what caused them, but not interacting themselves. And so when we have something like HARP that can make these coarse waves for us, we can then say, we know exactly what that wave looked like. We know exactly how it was generated. And so we can see how it impacted the radiation belts. So by, whether we make a giraffe or if we make just kind of something more like the hiss and the kind of bursty things, that should have a different how it interacts with the particles and what particles we see being precipitated. And so then we should be able to actually see what happened. Was our theory right? Did that work? And with HARP, we have an instrument on some satellites that are able to generate these waves as well. And so we try to do that. The other way that the atmosphere probably has changed is more on the timescale millennia, how much oxygen was in the atmosphere, how much nitrogen, and then that can cause impacts. But we haven't necessarily studied that as much. We do study a lot of comparative magnetospheres. So we compare how Earth's magnetosphere and atmosphere are either similar or different to, say, Jupiter or Saturn, and how that compares to the remnant magnetic fields and the atmosphere on Mars, and how that all is either similar or different. And that's another way that we can kind of learn about how these different phenomena on Earth actually are impacted and how they impact each other. So I hope that sort of gets to the question. I don't know, Chris, did you have another thought along those lines?
I was just going to say, and going back to the active experiments, I mean, we can also use to look at thickness of ion. So that's kind of a new area, like as Alexa mentioned, that we have one of the spacecraft that we showed data from tonight was Cluster, and it had an active experiment on it called Whisper, and it was a plasma sounder, and it was basically trying to determine the plasma density by using waves. And then we can have these planetary science use radio waves to look at thicknesses and things like that. So, and just probe things. So yeah, it's kind of a cool thing to do.
Just probe things. I like it. Just probe but to sort of circle it all the way back around, it's not like 20 years from now we're going to come back and say, oh no, all those TV shows we pumped into space destroyed our magnetic field, and now the Earth's atmosphere is being stripped away. That's not the same sort of effect as maybe emissions on Earth affecting our more immediate atmosphere, right?
No, in millions of years, when we finally no longer have, like tens of millions of years or however many millions of years it's going to take, when we no longer have a magnetic field, then the solar wind might start stripping away the atmosphere like it does at Mars.
On Mars, right.
Yeah, and so as the sun heats up the atmosphere, the ions and become charged, the molecules break apart. And when they're charged, they now will follow a magnetic field. And so if they happen to see the solar wind, which has a magnetic field,
they go away with
then
it.
they'll follow that.
but
But
it's
that takes a very, very, very long time.
gotcha.
And our magnetic field is going to be here for a very long time as well.
It's not like the Martians destroyed their magnetosphere by watching too much TV or anything like that.
Yeah.
Like that's not the mystery of Mars or anything. Okay, let me grab some more. We've got about 10 minutes left, about 8 minutes left. Noises. Here's a good one. Berkeley D asked, does the sun leave any sort of trace while it's cruising in space? So the sun, we were talking about the heliopause, right, and the heliosphere and all that sort of stuff. And that, I'm going to say, is it sort of teardrop shaped? It's got sort of a tail on one side and it's got sort of a bow on the other side.
Yeah, it's probably more round than our Earth's magnetic field, but it probably also still has these, one surface is probably more pushed in than another
in
side.
Or something like that. Gotcha. So
it's really hard to know because we don't have that many measurements.
it's hard to look back from the outside down at the Earth or the sun because, I mean, from outside the solar system, because we don't have a lot of spacecraft outside the solar system, right?
Yeah.
We do have models, and the models show that it's pretty contained, like what we had. But its magnetic field sometimes reconnects and will send out a plasma bubble, so a bunch of stuff out through the tail. But it typically seems to get mixed in with the rest of the solar wind pretty early on, I think, although, I'm not sure we've had too many measurements to look at that anyway. But, the sun maybe, but I think, we don't know. And I don't think, I haven't modeled those myself, but it would be interesting. Maybe that's something you guys who've modeled the heliosphere come on and try to do all of that. How do you imagine and model something that we can't see?
Yeah. So what I'm hearing is we need more funding for things like modeling that, and we need more spacecraft to launch, right? So that we can get more data. Those sound like good things?
More spacecraft.
That works for me.
It works for y'all. All right. Let's see here. More. Are there a website or these space sounds in it? Where can I find more space sounds online? Just over and over again. Here's another one. Why were there beeping sounds? And I think it was the Jupiter one. I'll play that again really quickly. So watch out, headphone users. But it almost sounds like a modem trying to connect. Has anybody piped this into like an old 14400 modem and just see if a signal comes through? It sounds like an old modem to me. Let me see if I can play it. So all the chirps and beeps, what's causing the chirps? And it is really loud in my headset. Turn it down a little. What causes those chirps and beeps? Do we know?
So when I was reading about that one, that there are actually waves in Jupiter's magnetosphere that are analogous to the waves that we have in Earth's magnetosphere, like the coarse waves. There could be some signals from the spacecraft mixed in there too, because all these electronics make noise.
Right.
I don't know if you noticed on one of the other I think it was on the Voyager video, there was a line across the middle that said interference, a big flat line in there, and like every spacecraft has these things, and that you have to, if you're a scientist looking at the data, you have to be aware of these things and either know how to filter it out or just ignore it. And so there could be some artificial stuff in there, but I think a lot of what we're hearing in that particular thing is because that one has been shifted in frequency and compressed. And so that kind of is maybe distorting things a little bit.
It makes me wonder, is this something that is recorded for a spacecraft before it leaves? So before launch, they put it in a special chamber and they listen to the spacecraft noises that the spacecraft's making before they send it on its way on its mission. So when it gets there, they could say, no, that's the spacecraft. We heard that bingly, bingly boop, or whatever the little wheeze is or whatever. Is that a thing?
That's exactly right. That's exactly right. And they do other tests, back and forth and Earth's magnetic field to see.
I think we got a little bit of, we're starting to lose your audio there a little bit. Let's see if it came back. Do we still have you, Chris?
Yeah, I'm here. I don't know if you can hear me.
Yeah, that's all good.
Is that we often do put our satellites and our instruments, even just the instrument by itself, into these magnetic quiet areas so that you can test and see what are different signals on there. And then you move them around to try to see, what happens there. So I remember studying some of these waves on a mission back in that was from the 1990s, called CRESS. And they did an orbit maneuver. And what that orbit maneuver did was it then ended up moving the boom that then started vibrating. Just like if you move, if you move something kind of around, it might take a while to settle in. So it just kind of oscillated back and forth for a while.
Right, like whoa, whoa,
So
whoa, whoa.
So all of a sudden I was going through and I thought I found this really cool signal. And then I looked at it, I'm like, that's way too regular. That looks not, that's too perfect. That's too good. And so sure enough, check the data and there's all these flags saying, yep, there was an orbit maneuver at this time. That wave is actually from the satellite itself.
No
and so
kidding.
then, to ignore that data, remove it if you can, so you can still look for other signals, or say, you know what, we're not going to use that time because it's too messy.
Yeah.
And then we'll go on to another event to look at.
And that's how sensitive some of the sensors on spacecraft that can detect this stuff have to be, because, they do an orbit maneuver, little thruster fires for a second, or they reorient the spacecraft, attitude change or something, and then there's an antenna that goes whoop, whoop, whoop. Like it has a little teeny tiny vibration. You might not even be able to see it, but it's just sort of settling back in, and that appears in your data. And like you said, if you don't know that that's something to look for, then you may think you've got something, but it's really just a little antenna boom that's wobbling and needs to take some time to settle down. I've never thought about that before.
And that,
go ahead, Chris.
And that, oh, sorry, I was saying that brings up some issues with designing these missions. So to measure electric fields, the main way people do it is they have a great big long wire antenna, and sometimes they have little spheres on the end, and the spacecraft needs to rotate so that these wires are held out. But for magnetic fields, they need things to be quiet. And so when they put those on booms, not so much because they need that long thing to make the measurement, but just to get the instrument itself away from the spacecraft. And all of the little computer things that are chugging away, processing data and all that on board the spacecraft. High voltage power supplies are a big thing that can cause noise that a magnetometer could pick up. I was going to say, what was there's another thing that I was just thinking of, because heaters. Some of these things don't like being cold, and so you have to have a heater on your satellite. And one of the things that on some of the stuff I've been working on, I have to be careful about the stupid heater on the spacecraft because it can make noise for me too. So
we had a magnetic field instrument on these balloons that we were launching, and we're flying them around Antarctica. And we couldn't get them too far away because we had to hand launch them. So having something sticking way, way far out while you're trying to run with 3 other people to launch a balloon, or sometimes 6 other people to launch a balloon, is that can become dangerous. So we had to keep it a little bit closer. But then we could see all of the signals for when we were actually sending the data back, and they happened every 2 seconds. And so you just had this nice thing. But then on top of it, you had this balloon that was flying in the stratosphere. And so it was like a pendulum itself, and kind of rotating and bouncing. And then every once in a while, you could see these winds come and pick it up and make it go faster. So all these things you try to test and measure before you go and launch it. Then you can try to remove it, and you then make sure that if you can't remove it, you don't publish something from the signal that then really just was, oh yeah, that's the data coming back down, from the balloon itself.
That's the transmitter, and you're hearing this. It's almost like, all right, I'm going to date myself, but even remember the old school Nokia phones, and if you had the Nokia phone near your computer and you had computer speakers, you knew when you were going to get a text because it go, and you could hear the transmission on your computer speakers before your phone would beep. It's the same sort of thing. Like the electronic devices doing these transmissions create interference that can be picked up by sensors like your computer speakers or your fancy equipment equipment that's on the satellites. But this is the coolest thing for me because I had never thought about this. We're out of time. We're so out of time. But I'd never thought. You think about testing a spacecraft, and you're launching this satellite. Wow, we got to make sure that the engines work, and we have to make sure that the solar panels unfold, and we got to make sure that the antennas all work, and all these things have to work. But I never, ever, I've been doing this for I don't know how long, and I've never thought we need to make sure we listen to the sounds the spacecraft are going to make, the electromagnetic sounds, the interference that the spacecraft itself is going to generate before we send it, so that we understand, oh yeah, make sure you know you're going to get this little blip of interference every time that this heater turns on or something like that. All the spacecraft that I've ever loved to think about, I've never thought about that. It's all the big stuff. Did the solar powers charge the batteries? Good, all right, send it. Well, no, you got a little bit more work to do.
Solar panels and charging, that ended up creating a current that was observed by the electric field boom. So now you have to remove that noise too, because that's every time that happens, right? So all these things. So data processing is a huge job that we don't thank people enough for, because without them knowing about all these little bits and then making sure to remove it from our data, we wouldn't be able to do it. That's a huge thing that we should give a massive shout out to all the people who take care of and curate all the data.
Absolutely. It's the thing. There's so many people that are involved in making things like this go off, and you don't always think about it. You're like, yeah, the rocket launch, that was fantastic. But all the things that have to come together to make missions like this successful so that we can keep learning about the universe that we live in. I'm going to get the entire band back together here really quickly. That's over here. 4 up. There's all of us. We are out of time. People always think I'm crazy. They're like, wait, you want to do a 2-hour show? You want to do an hour and a half show on what? You'll be bored after 15 minutes, and here we are. We've been talking for an hour and a half, not including the pre-show. We could continue talking, but it is the end of our show here this evening. Thank you all so much for the time today. This was absolutely fantastic. Dr. Alexa Halford from NASA up there. I'm pointing. See, I can look and point in the right direction. And then Dr. Kristine Sigsbee from University of Iowa. Thank you all so much for the time. It was fantastic to have you all on Virtual Astronomy Live here.
Thank you so much for having us. It was really
Yes, thank you.
Absolutely. And then, of course, our moderator, Summer Ash, over on this side. Summer, as always, it's a pleasure. Did you learn some stuff?
I did. And also, it's not in space, but fun fact, I think the radio telescope in Australia, Parkes, grad students using the microwave there messed some data up. Well, actually, I think they thought they discovered something, which it was
the microwave.
my professor effectively planted. He put a magnetic field instrument out in his field in the farm, way out in the middle of nowhere in Minnesota, and you could see when the cows come by and when trucks would come in, and it would look pretty, that's not much happening, and so it'd be nothing, and then all of a sudden there's a blip, and he'd go, oh yeah, that was when the tractor came by.
Wow, all right. I gotta say this. Your baby out there in New Mexico, the Very Large Array Summer. When I went there, I went to the open house, which they used to do twice a year. World's a little bit different now, but hopefully that gets picked up again in the future. I went out there, and they were like, "All right, electronic devices, turn off your cell phones, turn off all this stuff because it could affect their data." And I'm like, "What? Come on! I'm just here for a tour." But for real, people carrying around electronic devices could affect some of your data at the VLA, right?
Yeah, like if your cell phone's on at the VLA, like it's like shining a flashlight into someone looking in an optical telescope.
Wow.
Like it would be the brightest thing there.
It would be the
radio waves that are so faint from space.
You ever call anybody out? You're like, "Hey, I can see. You see this graph here? That's your cell phone. I'm trying to listen to the stars.
You have someone dedicated to that.
There's someone dedicated to that. Nice. Yep. Okay, we could continue talking forever, but we do have to wrap up the show. We're 5 minutes over. So thank y'all so much for the time. We've been doing these once a month. We do have one coming up next month, y'all. Let me see if I did this correctly. Next month, on December 17th, we're actually going to be talking about space flight in gaming. And if there's any Ultima fans in the house, we are going to have a very well-known nerd on the show with us next month on December 17th. So be looking out for that one coming up. But this is going to be the end of this month's Virtual Astronomy Live Sound in Space. Alexa, Chris, Summer, thank y'all so much. A fantastic show today, and we will see y'all next time. Thanks everybody in chat so much for joining us for Intrepid Museum's Virtual Astronomy Live.